Okay, today we'll take a look at a couple more properties of the conic sections, and then we'll get into some details, how to work with them, how to find equations, or how to graph. Now, one of the properties, one of the terms we use for conic sections is eccentricity. And eccentricity, well, in general, it kind of gives us how curved or how flat the conic sections are. Well, other than the parabola. Parabola, we don't really define the eccentricity this way. But eccentricity for both the ellipse and the hyperbola is defined as C over A. And the value of that will show us how, well, with an ellipse, how close to a circle the ellipse is, or how flat the ellipse is. So for an ellipse, think about C and A. C is on the inside from the center out to the focus, and then A is from the center on out to the vertex. So A is going to be bigger than C. So eccentricity will be somewhere between 0 and 1. And the closer it is to 0, the closer it is to be in a circle. Now, eccentricity shows up when astronomers talk about the orbit of the Earth and the other planets. The orbit of the Earth is an elliptical orbit. But at first, scientists thought it was a circular orbit. Well, it's very close to circular. The eccentricity has been estimated at about 0.0167. So that's pretty small. That's pretty close to 0, but not exactly equal to 0. If eccentricity equals 0, then we're talking about a perfect circle. Okay. Some of the other planets, you look up, they calculate eccentricity of all of them, and they all run from about, well, Mercury is a little over 0.2, and then the smallest one, well, the smallest one that they list in this source is Neptune, which is 0.0086. So that's almost exactly a circle. Not quite, but this tells us kind of how round or how flat the ellipse is. The closer to 1, the flatter the ellipse is. Now with the hyperbola, again, the eccentricity is calculated C over A, but with a hyperbola, C is bigger than what A is. So eccentricity is going to be greater than 1 for a hyperbola. And I guess technically they have defined eccentricity of a parabola, but in that case, any parabola, all parabolas have eccentricity of 1. So it's not real interesting to look at the eccentricity of a parabola. But there are ways that, things that we talk about with eccentricity of a parabola. But this is one property of the conic sections. Another property is the reflective property, and we'll talk about that here in just a second. For a parabola, we look at the vertex and the focus, and the reflective property says anything that is coming into the parabola is reflected to the focus. The way the shape of the parabola is, any beam or, well, light beam, sound beam, whatever, comes in, hits the parabola, and is reflected to the focus, no matter where that beam comes from. Now, we actually see parabolas, well, three-dimensional parabolas, which would technically be paraboloids, but we see paraboloids in certain things that you probably didn't realize. Satellite dishes, okay, the signal comes in and bounces off the side of the parabola into the focus where the receiver is set. Another thing that this property allows us to do, it's kind of the opposite direction. What about a flashlight? The bulb is set where the focus is, and when the light comes out, oh, that's a nice one. When the light comes out of the light bulb in all different directions, it is reflected where all of the light beams are parallel, and thus we have the flashlight, the light coming out of the flashlight is focused so we can see out in front of us. Now, that's probably the easiest one to talk about with the reflective property, but the ellipse also has an interesting reflective property, and that is anything that is emitted from one focus, no matter what direction it's emitted, it bounces over, it reflects to the other focus. And another property on that, if something is emitted at one focus in all directions at the same time, it will end up, even though all these, I guess, particles or waves or whatever you want to say is emitted from one focus, all of them arrive at the other focus at the same time. And this has been used in medical equipment where, to break up kidney stones. Somehow they've got it set up to where something is emitted from one focus, and through this elliptical, again, it's not just two-dimensional, but three-dimensional ellipsoid, it bounces all of this, whatever's been emitted, to the other focus where the doctor places your kidney, hopefully the kidney stone, and because it arrives at the same time, it will break up that kidney stone. Or at least that's hopefully what happens. Sometimes it does, and sometimes it doesn't. If it doesn't, then they have more problems to worry about. But once in a while that works, and we see that reflective property used in a medical setting. So a couple interesting properties for the conic sections. And now we'll take a look at some examples how we use this information, finding equations or graphing. Okay, we'll just pick some off of our worksheet. Problem number 30, find the equation of an ellipse with vertices at 0, 3, and 8, 3, and then eccentricity of 3/4. Well, to get an idea what type of ellipse we're dealing with, let's go ahead and plot the vertices. And let's see, 0, 3, and 8, 3. Well, immediately that should tell us which type of ellipse we have. Will we have a horizontal or vertical major axis? Okay, horizontal. Our ellipse is going to look something like that. Vertices are the outside edge of the ellipse, and well, the standard form for a horizontal major axis, x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. One major thing with finding the equations of any of these is find that main point hk. Now in the parabola that would be the vertex hk, but with the ellipse and the hyperbola that's the center. So where's the center of this ellipse? How would we find that? Okay, 4, 3. We look at our vertices, and the center is going to be halfway in between. Vertical, or horizontal, I guess. Horizontal, it's going to be at the same y value. The x value will be halfway between your vertices. So center of 4, 3. So that makes life pretty easy with that part of it. Now we just have to find A and B. Well, what is A? Okay, A, remember, is the distance from the center to a vertex, and we just found that to be 4. So A squared, 4 squared, we'd have 16. And then usually the last thing we'll be able to find is what B squared is. The other information that we're given is this right here. Eccentricity is defined as C over A. Now, in this case, A is 4. Okay. So C will be 3. Now, we don't always get that luxury of the denominator equaling the value of A. Maybe we have an eccentricity of 5/12, something like that, where A could still equal 4, but it's not going to equal the denominator of the eccentricity. But you can find what C is from that. But in this case, pretty easy. C is going to be 3. And then we have our relationship between A, B, and C. A squared is equal to B squared plus C squared, or however you're remembering that. I always have to think, okay, the largest one is going to be by itself. With ellipse, A is the biggest one, and so A squared is going to equal B squared plus C squared. Now on a hyperbola, C is going to be bigger than A, so that one, C squared equals A squared plus B squared. That's on a hyperbola. Here on our ellipse, well, we know A squared, C squared. So 16 minus 9 will be B squared, which is 7. Now, not all the time will we have nice, perfect squares down there. I guess 7 is a perfect square of square root of 7, but not perfect square integer squared necessarily. But that's the equation of the ellipse that would fit these properties. Questions? Okay, in number 38, we're going to look at the equation given to us, and they're asking us to sketch the graph of the hyperbola, well, after finding a whole bunch of stuff. But we've got some work to do to get this into the standard form. And the biggest amount of work is this right here. The y part, we do have that as a perfect square. Y squared, that's the only y part. So at least pick something somewhat easy for you. But the x part, we're going to have to complete the square to get it into x minus h quantity squared, which it becomes a lot more difficult because of the coefficient. To complete the square, we have to have 1 as the coefficient of the squared term. Well, that means we're going to have to factor out negative 16. That'll leave us with x squared, but then what? Minus 4x. Okay. And then here's a little trick as well. We're going to be adding something to complete the square, but technically whatever we add here, we have to multiply it by negative 16. Okay, that is what we're actually adding. So to kind of help not get caught up with that, what I like to do is say we're going to add something and subtract something all together and then see what happens with the negative 16. And then, well, another thing with the hyperbola and ellipse, let's move that 208 to the other side. Add 208 to both sides. This is our same equation, but in a form we can actually get to the standard form. What do we need to add to make this a perfect square? Remember the perfect square process, 1/2 of b quantity squared. And that would be negative 2 quantity squared. Of course, that's 4. And then minus 4. Now I showed this part here, although I think you guys could do that in your head. I hope so. But that actually helps us when we factor this into a perfect square, because that's going to turn out to be x plus whatever this is before we square it. So x plus negative 2, well, again, I think you can do that one in your head without worrying about that property, but it still fits. This factors into x plus negative 2, or we usually say x minus 2 quantity squared. Now, again, that's only this part. We still have the minus 4 on the outside, and then all of that is still going to be multiplied by negative 16. Okay. And then multiply through. Negative 16 times negative 4 is positive 64. Then subtract 64 from both sides. Let's see, that's going to be what? So we get 144 on the right side, and our equation then looks like y squared minus 16 times the quantity x minus 2 squared equals 144. Well, our standard form for both the ellipse and the hyperbola, it should equal what? 1. So we're going to have to divide both sides by 144. Which basically means divide each term by 144. And, well, there's nothing more to do on the first part, but we can simplify the second part here. We end up with what? So 144 divided by 16, we get 9. That simplifies to the x part over 9 equals 1. Okay, we finally got it into standard form. Now, from that standard form, we can find all kinds of things. First of all, the center. Well, that's going to be what? That's your h and k. Well, k doesn't show up, but 0, y minus 0 is still y. So, let's see. Foci, well, what we need there are the values a, b, and c. A is going to be what? A is going to be 12. Now, one thing with the hyperbola, a squared is always the denominator of the positive part. In the hyperbola, we have one part minus the other part. And whether this is bigger or smaller, it doesn't matter. That's going to be a squared. So then b squared is 9, so b is going to be 3. And then from there we'll find c. I guess really we need a squared and b squared to find c squared. C squared is going to be a squared plus b squared, which is what? Oh, nice value of 153. So c is going to be square root of 153. Which may or may not simplify. Just get a decimal value, get an approximation there's going to be good enough. But to find our exact points of the foci, we can use the square root of 153. It's essentially going to be, well, at this point we need to figure out, do we have a vertical or a horizontal major axis? That's from the y squared being the positive part, that'll be the vertical. So our vertices will be above and below the center. Okay? And the foci above and below the center. So the vertices, well, that's going to be A from the center. We're going to have to scale down a little, or scale up. We're not going to want to use 1 for our units. So center was 2, 0. We can use 1 horizontally, but vertically we'll need to change our scale a little bit. Maybe go 4. So vertex, and then to graph this, what we can really do, using A and B, there's a lot more formal ways to do this, but what I like to do is from the center, we go horizontally then B, and what was B? 3? Now, graphically, the scale is going to make it a little distorted, but what I would do from this is make a little rectangle that goes through of course, the vertices, and then find out where the minor axis would be and draw that. Now the hyperbolas are going to have what are called asymptotes. They will be slant asymptotes. So we'll have a line, a diagonal line that goes through the corners of this square and through the center. And then to sketch the graph of the hyperbola, those asymptotes, the hyperbola will get closer and closer to those straight lines as x approaches infinity and negative infinity. Now that's the bottom. The top, I'm not going to be able to get a little bit of the graph on there. So that's how we graph the hyperbola. And you can figure out the equations of the hyperbola or of the asymptotes, and sometimes you may have to deal with the equations of those lines, those asymptotes, but it's basically the line, the slope of the line, we're going up and over. So notice in this case we're going up A and over B, and then you got to find where your y-intercepts are, but from that you can find A and B based on the slope and where the center is. But anyway, our graph will involve the asymptotes. We didn't graph the foci, but from here we go up and down square root of 153, whatever that turns out to be. So probably somewhere up in that neighborhood and down here. Fairly close anyway. Okay, so that's our hyperbola, finding the center, foci, and vertices. And as well, we may have to do that with the ellipse or even the parabola. Depends on what equation, what form of the equation we're given. So all those different standard forms for the parabola, ellipse, and hyperbola, all the properties that we have, we can now find the equations given certain characteristics, or given the equation, find all those different characteristics and sketch the graph.